Hello and welcome. My name is Philip Rittiger. I'm a senior software engineer at Anaconda, and I build open source tools for visualizing data and building dashboards. Today I'm going to be introducing you to visualizing geographic data in Python. Before we dive into actually visualizing some data, let's get a quick overview of the various software libraries involved in doing this in Python. The main libraries that have been used in the past for visualizing data were matplotlib and basemap. Basemap was an extension for matplotlib, which allowed plotting geographic data and projecting it. This has been replaced by cartopy in recent years as basemap has been deprecated. And cartopy provides all the same features for projecting between different coordinate systems and plotting with matplotlib. In terms of visualization libraries, matplotlib is still a big standard. However, it only supports outputting static plots, while many more recent libraries allow outputting interactive plots, which allow you to zoom and pan and get all the best features out of the web technologies. One such library is Folium, which builds on Leaflet.js and produces interactive HTML output. Unlike IPyLeaflet, it doesn't support richer interactivity, such as calling back into Python to pull up another plot based on some interaction, or displaying additional information on other selections. It also requires Jupyter. We're going to be focusing on two libraries in this introduction, which is GeoViews and hvPlot. GeoViews is built on cartopy and bokeh and matplotlib, and hvPlot builds another layer on top, which provides a familiar API to users of the Pandas plotting API. Before we dive into actually dealing with some geographic data, we're also going to have a quick look at the various data libraries which are used for loading geographic data. GeoPandas is very popular as it extends pandas with support for geometry data. So we can load data from shapefiles or GeoJSON files. Additionally, Xarray is very useful for loading raster or gridded data, such as is used in satellite imagery and so on. Okay, so let's actually dive into some of the basics. So we're going to start by explaining a little bit about coordinates reference systems in the cartopy library. A coordinate reference system describes how we map data points on the spherical globe onto a 2D surface, i.e. our screen or a printed output. Cartopy provides a module called CRS, which stands for Coordinate Reference Systems, which provides a range of coordinate reference systems to use. So the most common that we're going to be encountering in this introduction, and even you more generally, are plot carré, which describes coordinates in terms of latitudes and longitudes, and Web Mercator, here called Google Mercator, because it's commonly used in the Google Maps applications. And we'll discover a little bit more about that later. So here we've declared a source and target projection, which means that we can start by, first of all, displaying these two projections, and we can immediately see the difference between these, right? The Web Mercator projection down here has distorted the latitude space near to the poles quite a bit. You can see here Antarctica is much bigger than it is here. And there's a huge discussion about which projection is best for different applications, particularly because it distorts different regions of the Earth very differently. And but we're not going to dive into that kind of controversy here. So here we're going to start by taking a single data point, the location of New York City in the US, and project that from our source reference system, the plot carré projection, to our Web Mercator projection. So if we run this, we can see here this transform point method allows us to transform this location from longitudes and latitudes to these eastings and northings, as they're called, which are meters away from the null point, i.e. this point on the equator, which is also called null island. So in this way, we can easily project data points, and in fact, the projections have various methods for projecting various types of data, including geometries, including images, and so on. Okay, so let's actually start dug into visualizing some data. So what we're going to do now is load GeoViews, and that's where we're going to start. Okay, so we've already discovered that we need to give our data points a coordinate reference system. We know the plotting interfaces need to know what kind of coordinates are these to put them on the map. The default projection that GeoViews uses is the plot carré projection, which allows us to display points in longitudes and latitudes. So here we're going to take these two data points, which is New York City and Beijing, and we're going to put it in this GeoViews points element. So we're just going to create a list with these two items in it. And then here we haven't declared this explicitly because this is in fact the default, but if we were to do so, we do say CRS equals plot carré, which tells GeoViews and the downstream plotting libraries how to deal with this data, how to put it on the actual map. Then we've got the second data point here, or this third data point, in fact, London, which is in fact expressed in terms of Web Mercator coordinates. And so again, we have to declare this. So here we again say CRS equals CRS.Google Mercator, and now GeoViews knows the projections of all three data points, which means we can now put it on top of a map. So if we execute this, we can see here that even though these coordinates are expressed in very different coordinate systems, they still appear in the correct location on the map. So here in New York, London, Beijing. So that was all pretty straightforward. We're going to dive, don't worry too much about the details here. We're going to dive into that in a little bit. Okay, so now we've discovered how to give our data a coordinate reference system which tells it what coordinates it is in. However, we might want to do the opposite as well, right? We might want to say, actually, I want my data to be projected to a different projection. So I want to display my data in a different projection than it is declared in. So here we've done exactly that. We take our city's longitude, city's Mercator, and tell it, basically project this to the so-called Mulvida projection. And then we get this nice globe, which is distorted appropriately because we told it to respect the aspect here. And it is, again, placed these in the correct places on this globe. So there's a wide range of projections supported. We're not going to go through them all here. And again, different projections have different trade-offs, particularly depending on the types of data and the location of the data that you're using. Okay, so one subtlety we haven't quite talked about here yet is the fact that by default, GeoViews will plot things in Web Mercator coordinates. And this is because tile sources, such as you would be familiar with from Google Maps, are generally defined in Web Mercator, right? And so by default, we therefore use Web Mercator coordinates because that allows us to put it on a tile source like this. And the really nice thing about tile sources like this is that they provide geographic context for your data and at varying resolutions, right? You can zoom down to an individual street, a little forest here in this case, or we can display it globally and it still provides geographic context, allows the user to zoom and pan around to kind of see where this data is located. However, when we want to project to some other projection, we run into an issue. The tile sources here are not defined in those projections, so we can't use them. In that case, we can use so-called features. Features in GeoViews provide geographic context in the form of a geometry. So here, for example, we've taken this coastline feature, and now we can project that to any coordinate system we want. So we can say projection equals CRS dot Mulvida again, and then it'll project it to our coordinate system. I should again say data aspect 1 so that it correctly stretches the globe in the way that the Mulvida projection expects. Okay, so that's not the only feature. GeoViews ships with a variety of different features. So here, for example, we're displaying the ocean, the land, the coastline, the borders, and this has taken a second. I'm not quite sure why it takes quite this long. But another thing we can see here, and which you may have noticed previously, is that, okay. So when we told it to project to Mulvida here, it inherited that projection down here, and that's why it took a little second to project all these different features to Movida. However, the other thing you will notice here is that we can use this multiplication operator to combine multiple elements and basically stack them on top of each other, an operation that we call overlaying. And so in this way, you can easily compose multiple elements and components together into a overall map. Okay, so hopefully now you understand the difference between these different projections and reasons why you might want to use tile sources and situations where you'll have to fall back to using a feature. Okay, so now let's actually plot some data. So far we've dealt entirely with the lower level GeoViews API. We're now going to be switching to using hvPlot. And so if you've ever used the .plot API on a pandas data frame, you'll be pretty familiar with this already. So the first thing we're going to do here is load the location of a bunch of airports in the US and display those. And as I said, it's very similar to the hvPlot, the pandas.plot API. So we simply call .hvPlot on this data frame. And then we're going to say we're going to plot some points. And in particular, we're going to plot the longitude and latitudes of those points. Then we're going to say, basically, this is a geographic plot, which is actually redundant with the CRS declaration. So we could just say, basically, this data is in plot Carré coordinates. And then we're going to display this, right? And so very quickly, you can see here within one line, we've got this plot which displays us all the latitudes and longitudes of the US airports around the world, in fact, in US territories. And so we can zoom and pan and get all the nice features of our tile source. So we can zoom in on individual airports and see where they are and get all the niceness there. So the other nice thing we can do now is we can also project this to a different coordinate system. So this time we're not going to be using the tile source for the same reason we discussed previously. We're just going to project it onto Movida, and that still works. Similarly as before, we've got these two options, basically the CRS to declare this is what projection our data is in, and the projection, which tells us which projection to display it as. Cool. Okay, so that's points, very straightforward. Let's now get into geometries. Geometries are another really useful type of data that you might want to display. And the GeoPandas library, as I mentioned earlier, allows you to load geometry data from shapefiles or GeoJSON or various other formats which are common, right? In this case, we're loading this example shapefile which ships with the library. So we've done that here, and as you can see here, GeoPandas just displays our data as a pandas data frame. In fact, it is a pandas data frame with this special column, the geometry column, which contains polygons which we can render. And so what we're going to do is create a so-called choropleth plot, which basically displays polygons for each of the countries in the world. And we've got this additional data. We've got the population estimate, the GDP estimate. And what we can do with that is compute the GDP per capita. So we're quickly going to do that, then scale it into a reasonable number that we can display on our map. And then we're going to simply say hvPlot that. We don't even need to tell it that it's polygons because GeoPandas declares that for us. Again, we're going to use some tiles. We're going to do some special sizing. And then we're going to color it by the GDP per capita and give it a title. So if we do that, we get this nice little choropleth plot, which gives us the GDP per capita in $1,000 across the world. So that's pretty interesting. And again, single line of code gave us this really nice plot. Okay, so now we've looked at points, we've looked at geometries. As I mentioned earlier, rasters or gridded data are another very common type of data. And to load that, we're going to recommend using the Xarray library. Xarray is basically the pandas for multi-dimensional arrays. And so here we've loaded this sample data set again. Usually this might be stored in a variety of formats, whether that's netcdf, ZAR, or any other range of formats, just such as GeoTIFFs. So all of these can be loaded very easily with Xarray. But here we've loaded this data set. We can see here it has 3 dimensions. It has a time dimension, it has an X dimension, it has a Y dimension. And so basically this represents air temperatures over time in locations across the world, in fact, across the northern hemisphere. And so, again, since we loaded hvPlot X-array, hvPlot simply understands this data out of the box. So we can simply say, basically overlay this on our coastline, and then basically plot a quad mesh of the X coordinates and the Y coordinates, and project this so that it doesn't have to project it every time we zoom and pan around. So we're going to see that in a second. Let's bring this plot up first. Okay, so now we have this plot of air temperatures across the northern hemisphere. You can see here we get the really nice hover information, so we can hover over any location and see what the air temperature was. And we've gotten this slider. So that's really quite interesting, right? Basically, the fact that we've told it we're plotting the X and Y locations has told hvPlot, I've got this leftover dimension called time. So what do I do with it? The only thing I can do with it, unless you specify anything else, i.e. you select a particular time, is give you a widget. And so with this widget, we can now scrub across this time dimension and see how the temperature evolves over time. The other thing we've done here is we've told it to rasterize this data. And so this is because really this data is relatively large and it's represented as a quad mesh, which is fairly inefficient to render. So rasterize tells hvPlot to basically re-rasterize this data into an image rather than a quad mesh, which is much quicker to display. And so this gets us directly into this next section about large data sets. The rasterization here happens using a library called Datashader. Datashader allows taking any really large data set and rasterizing it into an image, which resolves as we zoom in and out. So if I zoom in here, you can see here, kind of it resolves a little bit more. There's not much more resolution than we saw initially, but if we had a larger data set with 10 megapixels or something similar, we'd see a lot more information as we zoom in. So basically, it only sends as much data to the browser as you're requesting at any one time, which allows us to deal with data sets much, much larger than could be usually handled in a browser. And so in this particular example, we're going to be loading the New York taxi data set. Basically, it's various New York taxi trips in New York City, i.e. their pickup location, their drop-off location, and various other information. And so if we look at this is quite a lot of data. So this is about 11.8 million data points. So if we try to display this using Matplotlib, that would probably be fine. It would take a while to render, but that's okay. But if we try to display it with a library like Bokeh or Plotly or anything that has to send data to the browser to render, that's going to really bog things down and in certain cases crash your browser. And so Datashader allows you to plot data in the millions or billions of data points and rasterizes it or aggregates it into a fixed size image, which can be sent to your browser. And as you zoom and pan around, it re-aggregates and gives you all the information that you might need. So here, for example, we now have this plot of New York City with all the New York taxi data trips. And as we zoom in, you can see here we can resolve individual pickup locations while still maintaining really interactive performance. Right? So we get the best of both worlds. We can view all our data, all these 12 million data points, while also maintaining good performance. All right, so I hope you've enjoyed this introduction. This is only one video in the series, and I hope you join us again. Thank you.